it will also be a summary of types of magnetism, magnetic anisotropy, and magnetic domains. So we have many types of magnetism. We have already seen diamagnetism, we have paramagnetism. Paramagnetism is split into many parts. Curie paramagnetism, Curie-Weiss paramagnetism, Van Vleck paramagnetism, Pauli paramagnetism. There are 4 types of paramagnetism. I will only show you 2 parts of paramagnetism. There are ferromagnetism, antiferromagnetism, and ferrimagnetism. So what is paramagnetism? I will shortly explain to you that except the diamagnetism, all types of magnetism has some net magnetic moment. Okay, this materials has magnetic atoms, and they have some magnetization if we apply magnetic field to these materials. In paramagnetic materials, atoms has net magnetic moment, but without external magnetic field, the net magnetization of the system is 0 because they are randomly oriented. Okay. In ferromagnetic material, we have perfect alignment of the magnetic moments. For this reason, we have huge magnetization. In antiferromagnetic materials, again, we have a perfect order, but they are ordered antiparallel to each other. For this reason, again, net magnetization is 0. In case of ferrimagnetism, again, we have a perfect order, but we have 2 sublattices. One sublattice is this one. They are ferromagnetically aligned, and the other one is this one. They are also ferromagnetically aligned, but A sublattice and B sublattice, this one, are opposite to each other. So finally, you should expect 0 magnetization, but not, because the magnetic moments of A sublattice are bigger than the magnetic moments of B sublattice. For this reason, we have some magnetization in the ferrimagnetic materials. These materials are very important in technological applications. These materials are very important in data storage industry. Okay? Okay, please.
What could be the visual representation of the diamagnetism?
Diamagnetism is present in every parts of this magnetic materials. For example, we have paramagnetic material. This material has atoms which they have magnetic moment, but if I apply external magnetic field, this material will earn a magnetic moment opposite to the applied magnetic field. This is the case also for ferromagnetic materials, ferrimagnetic materials, antiferromagnetic materials. In diamagnetic, I am not talking about diamagnetic atom, I am talking about diamagnetism, okay? If you are talking about diamagnetic atom, it means that there is no magnetic moment, okay? The material has closed shell, okay? No net magnetization. But if you apply external field, then you will have magnetic moment opposite to the applied field, right? And this effect occurs every type of magnetism, okay? In addition to this magnetism. But since the susceptibility of diamagnetism is very small, it is shadowed by strong effect from these magnetization types. Is it answer to your question? Okay, then if you have, we can discuss later on. Okay, the first systematic susceptibility measurements done by French physicist Pierre Curie and published in 1895. He has done temperature-dependent susceptibility measurements, and he found that paramagnetic materials has this susceptibility relation. So, if you increase the temperature, then susceptibility and magnetization drops. You can see this plot here. This is temperature, and this is susceptibility axis, and this is the susceptibility of paramagnetic materials. You remember from the first lecture, it is negative and temperature independent. But in case of paramagnetic materials, you have this type of relations. It means that at 0 Kelvin, if you put here 0, then susceptibility goes to infinite, okay? If you increase the temperature, then the susceptibility decreases. But what happens, for example, here we have a paramagnetic material, we have magnetic moments, they are not interacting with each other, and they are randomly oriented. So net magnetization is 0. What happens if I apply external magnetic field? This field will act toward on this magnetic moments, and I will have some certain alignment of magnetic moments, right? But what happens if I heat this material? If I increase the temperature, thermal agitations would like to make this magnetic moments randomly oriented. So, magnetic field would like to align the magnetic moments, and temperature will work against the magnetic field. Okay? So you can see it from this curve.
Why it doesn't go to 0?
Sorry?
Why it doesn't go to 0?
Yeah, actually it goes to 0. But it is question of the sensitivity of your device. Okay, so the measurement done in 1895 and theoretical calculation came 10 years later in 1905 by Paul Langevin, and he found this relation for the paramagnetic materials. This is the magnetization of paramagnetic materials. This is N. N means number of atoms per unit volume. Mu is the magnetic moment of atom. And this is the Langevin function, which is given by cotangent hyperbolic A minus 1 over A. And A is here given by mu times H divided by KT. Mu is magnetic moment of atoms, H is external magnetic field, K is Boltzmann constant, and T is the temperature. So, if you increase the temperature, you get small a. If you decrease the temperature, you get big A, okay? For these two cases, the behavior of the paramagnetic material will change. For example, here, if you have big A values, for big A values, this Langevin function goes to 1, so magnetization will be M0. Here, I would like to remind you another misunderstanding between M0 and MS, saturation magnetization. For the saturation magnetization, in some books you see M0, like this one, okay? But in some books, for the saturation magnetization, you will see MS, okay? So what is the difference in between? Who knows?
This is that when all the spins are aligned along the direction of external field.
Right.
That is saturation magnetization.
But what is M0?
M0 is spontaneous magnetization. What is the instantaneous magnetization, which is available in the magnetic material according to the applied field?
The first one was correct. Actually, they are more or less same thing. MS means saturation magnetization, which means that you get the maximum alignment of the magnetic moments, okay? But at certain temperature, for example, at 300 Kelvin or 5 Kelvin. And 0 means saturation magnetization at 0 Kelvin, okay? At 0 Kelvin, there is no thermal agitation, okay? There is no force against the magnetic field. So you can get perfect alignment at 0 Kelvin because there is no thermal effects. So, and 0 is saturation magnetization at 0 Kelvin. MS means spontaneous or saturation magnetization at certain temperature. Okay? This is the difference in between. Okay, so I have told you that at big A values means we applied very huge magnetic field and the temperature is very low. So what do you expect? We can able to align the magnetic moments. So the magnetization will go to saturation, okay, this curve. But for small a values, we will have a Langevin function will be equal to a over 3. And if I put this Langevin function for small a values here, finally I will have this relation for the magnetization. This will be, let's say, a solid line. Okay. So saturation occurs if we have big A values. For this reason, we need high field and low temperature. For small A values, magnetization changes linearly depending on the age. This is the behavior of paramagnetic materials. So you increase the magnetic field, magnetization increases. You decrease the magnetic field, magnetization decreases. And this is the mass susceptibility of the paramagnetic materials. Here I have N. N is the number of atoms in unit volume. This is given by Avogadro's number times density of material divided by atomic weight. If I put this term here, finally I will get this expression, Avogadro's number mu squared divided by 3 AKT. Please look at this formula. This is constant, right? Mu is constant for certain atom. Atomic weight is also constant for certain atom, Boltzmann constant, and only changeable parameter here is the temperature, okay? So I can collect all this constant for this material in this big constant. This is called as Curie constant. So what Langevin did, he found this relation, which is first found experimentally by Pierre Curie, okay? He theoretically calculated this expression. So what you can get, for example, you measured your material and you measured this type of behavior, okay? And you found the susceptibility, okay? You know the susceptibility and you know the Avogadro's number, you know the atomic weight of your material, you know the Boltzmann constant, you know the temperature, then you can calculate the magnetic moment of your material, okay? This is done and this is valid even in today, okay? This is commonly used method to calculate the magnetic moments of paramagnetic materials. This is very useful formula. Okay, and let's come to Curie-Weiss paramagnetism. The other one was Curie paramagnetism. So what is the difference in between? In Curie paramagnetism, we have many magnetic moments and there is no interaction in between. But in Curie-Weiss paramagnetism, these magnetic moments also interacts each other, okay? So this is the only difference. Due to this interaction, susceptibility does not go to infinite at 0 Kelvin. It goes at higher temperatures. It is here. So the susceptibility of the Curie-Weiss type of paramagnetic material is given by C over T minus theta. Theta means Curie temperature of the material. Until after theta, we have this type of behavior as we observed in Curie type of materials. This is Curie law. Susceptibility goes to infinite at 0 Kelvin. This is Curie-Weiss law. Susceptibility goes at theta value. Okay? And theta shows us that the magnetic moments are interacting each other also in paramagnetic materials. But many of the paramagnetic materials obey on this Curie law, okay? Not Curie-Weiss law. But Curie-Weiss law is also very important to explain the mechanism in ferromagnetism, antiferromagnetism, and ferrimagnetism, because all this type of other magnetisms, we have magnetic interaction between atoms, okay? Here I can summarize 3 types of magnetism. We have diamagnetism. This is temperature independent and it has negative susceptibility. We have Curie paramagnetism, this one, and this is Curie-Weiss paramagnetism. In some books, you can see temperature versus reverse susceptibility curves. Instead of susceptibility curves, they define same things. Okay, so, but all these theoretical explanations to paramagnetism and diamagnetism done by the classical mechanics, okay? In order to get good agreement between the theory and experiment, we have to do quantum mechanical corrections or treatment of the classical theory, okay? the result will not change, okay? We will have this type of behavior again, okay? We will have this type of behavior. So quantum mechanics will not change the results of classical theory, but it will only increase the agreement between theory and experiment, so we will get good results. Okay, in quantum mechanics, we define the magnetic moment with G factor times J times 4 magneton. J is total angular momentum quantum number. G is this G factor or spectroscopic splitting factor. It can be calculated by the Landé equation. This is for the expert. You can see lecture notes later on. And here we have J. J is total angular momentum, can be calculated by Hund rules. Who knows Hund rules? Hund rules, okay. So, there are 3 rules. The first one is that Hund rules defines that how we can put the spins in the orbits, okay? This is the duty of Hund rules. So, there are 3 rules. First rule, total spin angular momentum must be maximum. Second rule, of course, we should consider Pauli exclusion principle. Okay. For example, you have 2 spins. You cannot put them in same orbit like this. Both spin up. It is not possible because Pauli exclusion principle against this. And the second one is total angular momentum. Total orbital angular momentum must be maximum. For this, we should consider the first rule and again Pauli exclusion principle. And the last one, we need this one, okay? Total angular momentum. Last one defines the total angular momentum. If the shell is less than half filled, which is given by L minus S. If shell is more than half filled, L plus S. And if shell is half filled, J is equal to S. And L is 0. Here I have an example. For example, you have 5 electrons. You have an atom, and this atom has 5 electrons in 4f shell. Okay. For 4f shell, we have Ml. Numbers are 7. Okay. So I will have 7 orbits. Okay. And each orbit will have 2 electrons. And finally, in totally, I should have 14 electrons in the 4f shell. But I have only 5 electrons, so I have to put them there. So then, Hund rules will help us, okay? What was the first Hund rule? Total spin S must be maximum. So, I should put these spins in same directions, okay? But in different orbits. Because I cannot put this one here in this position because Pauli exclusion principle does not allow this. And then I have 5 electrons here, I put them, but what about total orbital angular momentum? For example, if I put this one here, then this will cancel this 2. Then the orbital momentum will decrease. So this is against Hund rules. For this reason, I should put them here to make the orbital angular momentum maximum. So, how to calculate them? I have 5 electrons, and each electron has 1/2 spin. So, finally, I have 5/2 spin contribution. And L is this -1 and +1 will cancel each other, and this is 0. So, finally, I have +2 and +3. So, L will be 5. Since the shell, 4f shell, is less than half filled, then I will apply this formula, 5 minus 5/2, and finally I have this J value. So when I put this J value here, I can calculate the magnetic moment of this atom. I can also calculate the G factor by using Landé equation because I know the J, I know the S, I know the L, okay? This is in this way. Okay, so average magnetic moment of atom along the magnetic field is given by this formula. This is very long mathematical explanations, I mean 3-4 pages. you can find all these expressions in the lecture notes of magnetic materials. They are already shared with you. So here I will summarize them. This bracket here is given as Brillouin function, okay? Depends on J and A value. You know A is given by mu times H divided by KT. Here I have G factor, Bohr magneton times J, and mu is given by G factor J Bohr magneton, and here I have, since I have here mu, I will take this mu, put here, okay, and then finally I have this A value. Okay, so this is my magnetic moment, average magnetic moment along the magnetic field. And this is for just one atom, okay? This, saat kaç?
Hocam buçuk.
Okay, I have 10 minutes. So this is for just one atom, okay? If I have many atoms in the material, then I will multiply with the number of atoms. So this is the number of atoms in unit volume. This is my magnetization. Okay, I will skip this one. So finally, I will get this susceptibility, okay? So what I have here, N times mu effective square divided by 3 kT. Mu effective is given here, okay, this one. We have constants here for certain material. I have constant here for certain material, Boltzmann constant, and I will collect all these things in one constant. So what I have done, I have got the experimental result of Pierre Curie. I have got the theoretical, classical result of the Langevin by quantum mechanical treatment. But now my formula includes the J value, which is very important in quantum mechanics, okay? In order to get good agreement between experiment and theory. So here I will summarize all types of paramagnetism and diamagnetism. So here you see van Vleck paramagnetism. You can see details in the lecture notes of magnetic materials. This is also temperature independent paramagnetism. Here you see Pauli paramagnetism. This Pauli paramagnetism comes from the convection electrons in metals, okay? Up to now, we are talking about core electrons, okay? Core electrons means they are bounded in the orbits, okay? They are traveling in the orbits around nucleus. These are the core electrons. But we also have free electrons or convection electrons in metals, okay? These electrons have also spin property, so they also should contribute to the magnetization, and their contribution is explained by the Pauli, and it is also temperature independent, but it is positive, very small compared to normal paramagnetism. I mean 1 million times smaller than Curie paramagnetism. And this Landau diamagnetism also comes from the convection electrons. I will not go into detail because my time is limited. So let's come to the ferromagnetism. Ferromagnetic materials are very important in technology, in magnetic hard disk drives, for information storage. So we pay lots of money for this type of materials, and it is developing very fast. So what you have seen here, that please look at this curve. This is magnetic field versus magnetization. For paramagnetic or antiferromagnetic materials, you increase the magnetization and you increase the you increase the magnetic field and increase the magnetization linearly. Okay, it is vice versa here in this direction also. But in ferromagnetic materials, it does not happen. For example, you start to increase the magnetic field. This is magnetization axis. Magnetization starts to increase, but this is not a linear way, okay? So once you saturate in C point, you saturate all magnetic moments along the magnetic field. And you rotate the direction of the magnetic field into the opposite direction, then you cannot follow this first way, okay? You can never come back again. This is the property of ferromagnetic materials. You can only follow this way. And here at D point, this is very important, why these materials are used in data storage industry. At D point, magnetic field is 0, right? But they have huge magnetization. Even without external magnetic field, this type of materials have huge magnetization. This is called as remanent magnetization or remanence. This is unique property of ferromagnetic and ferrimagnetic materials. And if you go further, you saturate the magnetic moments in opposite direction, so it follows a symmetric way. So this is called as hysteresis curve of ferromagnetic materials. Ferrimagnetic materials behave also in this way. And this is the temperature dependence of the magnetization of ferromagnetic materials. In periodic table, we have 3 ferromagnetic materials at room temperature. Iron, cobalt, nickel. They are 3D metals. And iron has huge magnetization compared to others. And it has Curie temperature around 1,000 Kelvin. 1,100 Kelvin. And cobalt has much higher Curie temperature, and nickel has Curie temperature around 600. So what is the meaning of Curie temperature? Who knows the Curie temperature for the ferromagnetic materials? Okay, only one person. Let me explain. Here we have ferromagnetic order, right? So all magnetic moments are aligned parallel to each other. What happens if I heat this material, if I increase the temperature? Thermal agitations would like to align these magnetic moments randomly, right? And thermal agitations or thermal effects will destroy this orientation or order, right? So I should expect some decrease in the magnetization. Indeed, it happens. So if I increase the temperature, magnetization decreases, right? But slightly. But at certain temperature, at Curie temperature, magnetization completely disappears and the material goes to paramagnetic state, okay? After Curie temperature, all ferromagnetic materials goes to paramagnetic state. Here, this is the behavior of mass magnetization divided by mass magnetization at 0 Kelvin. This is also called as normalized magnetization. This is the normalized temperature. Temperature normalized by the Curie temperature, and it contains a J value. If I plot this curve for some different J values, for example, J1/2, J1, and J infinite, what is the meaning of J infinite? The main difference between quantum mechanics and classical mechanics is that the energy is increased, okay, in quantum mechanics. So you cannot give infinite values in quantum mechanics, okay? You can only give discrete values, right? So if you put J is infinite here, it means that you have classical result, okay? If you have J1/2, it means that you don't have any orbital contribution, you only have spin contribution. And in ferromagnetic materials, orbital contribution is quenched, so we only have spin contribution. So I can expect that this J value will perfectly define the behavior of ferromagnetic materials. So let's plot 3 curves for this one, and this one. So this outer curve is given for J1/2, and this one in the middle is given for J1, and this is for J infinite, for the classic. This is theory, okay? And I do experiment. I change the temperature, I measure the magnetization for 3 ferromagnetic materials, for iron, cobalt, nickel. This open surface shows the iron, okay? And this squares show the cobalt and nickel. So you can easily see here that the experiment follows this curve. J is equal to 1/2. This is the real behavior of ferromagnetic materials because the orbital contribution is quenched in ferromagnetic materials. Okay, this is the results of molecular field theory for ferromagnetism. Magnetism disappears at Curie temperature, and after this temperature, susceptibility behaves like paramagnetic materials. How many minutes do I have? 5. 5 minutes. Okay. Let's talk about magnons. Magnons are also known as spin waves. In reality, what we know that in ferromagnetic materials, all spins are aligned parallel to each other, right? This is in theory, this is assumption. But what about in reality? For example, the temperature here is now very high, right? Around 300 Kelvin. So I should expect some thermal agitations, thermal effects, if I have ferromagnetic material here. So the spins will not be perfectly aligned. I cannot expect this because the temperature is very high. I should have some thermal effects. Okay? So what is the thermal effect? For example, here at the beginning, without thermal effect, I have spins perfectly parallel to each other. If I excite one of the spins in the chain, for example, change the position of one spin opposite to others, can I do that? I cannot do that. Exchange interaction does not allow us to do that, okay? But I excited this because I gave energy to the system. I heat the material. So it must give some result. This excitation will be shared by the neighbors, okay? So instead of changing one spin direction in the chain like this, what I do, I share this excitation with other atoms. It's like this, okay? So just one rotation shared by the neighbors. And this behavior is in waveform, okay? You can see from this. Of course, for the details, we have to discuss a lot of things, but the time is limited now. So it is, I think, enough. So, but I can easily expect that any thermal effect should decrease the ferromagnetism, should decrease the total magnetization, right? So how it occurs in mathematics? So this is my total magnetization, n times mu. Mu is given by G, J, Bohr magneton. Instead of J, here I use S because for ferromagnetic materials, J is close to the S. This is the saturation magnetization, but each magnon occurs in the system, decrease the magnetization with 1 G Bohr magneton. And finally, this decrease after some calculations can be given by this formula. So this magnon's spin waves explains the behavior of ferromagnetic materials here. So this decrease in the magnetization occurs by temperature with the relation of T over 3/2, okay? If temperature increases, then we lost the magnetization with this relation. Okay, let's come to antiferromagnetic materials. The theory done by Neal in 1932, again by the molecular field theory of Pierre Weiss. Maybe none of you heard about these materials, and some people consider that they are not important. But in magnetic hard disk drives, without these materials, you cannot read the information. Okay? very important material. So behavior of susceptibility for these materials, they have nil temperature because nil explained. Nil temperature means that this antiferromagnetic order destroyed after this temperature. After nil temperature, material behaves as paramagnetic. But below the nil temperature, susceptibility goes like this, because antiferromagnetic ordering starts and magnetic moments cancels each other and it decreases. Okay? And since they have anti-parallel alignment, these materials has negative theta value. Okay? Another type of ferrimagnetism, they are very important materials in industry. They have this type of relation. This is temperature, this is magnetization, this is ferromagnetic iron, this is ferrimagnetic material. Okay? They are similar to the ferromagnetic materials, but completely different materials. And this is the susceptibility behavior. In ferromagnetic materials, reverse susceptibility is linear with temperature, but in ferromagnetic materials, they have, ferrimagnetic materials, they have this type of behavior. And the ferrimagnetic materials have also hysteresis curves like ferromagnetic materials. There are two important classes of ferrimagnetic materials. One is cubic ferrites, and the other one is hexagonal ferrites. Hexagonal ferrites have very huge anisotropy. For this reason, they are commonly used in industry, okay, for the magnet production, in toys, in motors, in electricity also. Cubic ferrites have this general formula. This M here, divalent metal iron, for example, manganese, nickel, iron, cobalt, magnesium, sometimes zinc, copper, okay, whatever. And then we have iron oxide here. If you have cobalt instead of metal, this is called as cobalt ferrite. If you have iron here, iron ferrite. If you have copper, copper ferrite. If you have zinc, zinc ferrite, okay, the name changes. So, what is magnetic anisotropy? Magnetic anisotropy is also important in magnetic data storage industry. There are many types of anisotropy. Anisotropy means that direction dependence of the magnetization. Can I take this one?
Yeah.
For example, you have this type of material, okay? You apply external magnetic field in this direction and you measure the magnetization. You apply the external magnetic field in this direction and you measure the magnetization. You apply external field in the diagonal and you measure the magnetization. If you see same results, your material is isotropic. If you see different results, your material is anisotropic in terms of magnetism, okay? So this is magnetic anisotropy, direction dependence of magnetization. But of course, there are many types of anisotropy and very, very important in industry, okay? You cannot see, but I see here lots of money, okay? So, the most important one is magnetocrystalline anisotropy. There's a shape anisotropy. It's the shape of the material, you change the magnetic properties. Surface and interface anisotropy, if you have very thin films at the interface and surface, you get very important effects on the magnetism. Induced anisotropy, for example, you anneal or you deformate your material or you irradiate your material, then you create anisotropy in your material. And this is unidirectional anisotropy, which is the mechanism in the read heads in hard disk drives, also in the magnetic ramps. And only the first one is the intrinsic property of the material. The others are due to shape or induced effects. I will skip this one. So what is the origin of magnetic anisotropy? The origin of magnetic anisotropy is spin-orbit coupling, okay? We have, for example, electron, okay? And this electron is traveling around the nucleus. It has orbit. So, and it also has spin. And spin and orbit interacts, okay? But in the lattice there are many other atoms, and this orbit and spin also interact with the lattice, okay? It is summarized here. There is an interaction between lattice and orbit, there is an interaction lattice and spin, and there is an interaction spin and orbit. So the main origin of the anisotropy is coming from between spin and orbit interaction. This is weak but very important interaction because due to strong interaction between lattice and orbit, it affects the spin-orbit interaction and it gives rise to magnetocrystalline anisotropy. Okay, let's come to magnetic domain walls. I have 3 or 5 slides. This is last topic. So, who knows something about magnetic domains? Are they important? Why? You have CDs, right? You have DVDs, or you have hard disks. You store information and read the information from this type of devices, right? How we can do that? We store the information in the magnetic domains, okay? Each domain means 1 bit, okay? So this is the source of data storage industry, magnetic domains. For example, of course, these domains are proposed by Pierre Weiss in 1907 in order to explain the ferromagnetism, and they observed in 1945 in the Bell laboratories. So, for example, here you have a ferromagnetic domain. In one domain, you have many materials. Okay, you have ferromagnetic order, and here there is a border or wall. And then here we have another domain, okay? Again, here we have ferromagnetic coupling, right? But what is the meaning of this domain 1 and domain 2? It means that if I have magnetization here along this direction, I can store it or code it as 1, and the other one is 0, okay? Depending on the orientation, I can make data storage. So what is the behavior of domain wall? Of course, there is no strict transition from one domain orientation to another domain orientation. In the domain wall, there are many atoms, many atoms, sometimes 100 atoms. For example, here we have one domain orientation, here we have opposite domain orientation. So in the domain wall, we have many atoms. Via these atoms, I can accommodate this rotation of the magnetic domains. For example, we can calculate the magnetic atoms here for the iron, okay? Iron is ferromagnetic material, and let's calculate how many atoms contribute to the domain wall in iron. This is the formula. So the thickness of this domain wall, the thickness of this wall in iron is around 400 angstrom. It means that 150 atoms, okay? In one domain wall of the iron, we have 150 atoms. And the angle between neighboring atoms, so the angle between this one and the angle between these two, the angle between these two is around 0.6 degrees. This type of behavior, just antiparallel orientation in the border, is not favorable in ferromagnetic materials because ferromagnetic materials want to align parallel, right? And it requires very high energy. In order to get this type of behavior, this energy shared by many atoms, okay? So finally, we can have parallel alignment, let's say a semi-parallel alignment of atoms. They only have 0.6 degrees in between. Okay, I will skip this one. So this is my last transparency. This is a hard disk. who have seen the inner part of hard disk? In hard disk, we have many disks like DVDs, but we can write both sides, okay? So we have some stacks of disks, and between the disks, we have read heads, read and write heads. So we store the information in these disks, in the hard disks. So this is the image of a hard disk done by magnetic force microscopy. So what you see some rectangular shapes. Of course, they are not homogeneous in shape. For example, of course, there is no domain direction resolution here. For example, here 1 bit, this 1 bit, this 1 bit, this 1 bit, and each of them carries one information. And this is another type of domain imaging done by Kerr microscopy. Here again, magneto-optical Kerr effect is used. So what you can see different colors, okay? There are no arrows normally. This is just for the presentation. You see different colors. For example, white color shows the domain direction in this way, and this gray color shows opposite direction. Okay, so via this you can get information about the domain positions, whether the information stored in 1 or 0 phase. Okay, I tried to summarize as possible, but of course there are some missing points. But since the time is limited, it is not possible to explain everything. I think you have learned something, or you remembered something. Do you have any question? Okay, thank you very much for your kind attention.
You know, it's your turn now. Nora is going to explain something about hotel, then we are going to have a tour.
Okay, so